Alfred, and you're listening to Dan's Cadre of Experts. I've got a guest who's also an old friend, Chip Arata. Chip and I have been working together for quite a while. We're going to have to reminisce a bit, and I'd like to thank you for coming on today.
Well, thanks for having me.
Let's see, if I recall correctly, it's probably, I don't know when it was, but I met you, we were both working at Vetco Gray.
Yeah.
With a fellow named Ted Williams.
Ted Williams, exactly.
And Ted was busy. We're sitting in the office and talking. It turns out we're both welding guys.
Yeah, I was there to sell him powder, and you were there to sell him a PTA machine.
It might have been a TIG machine for all I know, because I wasn't doing much plasma transferred arc at the time, and that's why I like having you on, is because I think you're a large part of the inspiration. You convinced us we could probably build plasma machines.
Oh, true. Yeah, it was a TIG machine.
Yeah, I think I was doing hot wire TIG, because Vetco's doing that. I don't know what you were doing with the plasma.
He was using cobalt-based number 12, and I was trying to sell him on-balls powder at the time. And you stuck your head in and said, I got to borrow this guy for a minute, and I'll buy you lunch if that's okay with you. And I said, sure. So you took Ted, did what you had to do with him. He came back. I did my pitch, and then I think the three of us went out to lunch.
Is that how? Okay, yeah, that's way back. That was what? Middle 90s or something? I don't remember.
Yeah, mid-90s.
When were you working for Anvol?
Yeah, I think it was still Anvol at the time.
Right. And so Anvol, let's tell the people what's going on here. So you're like a powdered metal guy. And so you have been in the powdered metal business forever. That means you do, lately I suppose that means additive manufacturing. Before that it was injection.
Well, we do metal injection molding powders, additive manufacturing powders, thermal spray powders, plasma transfer arc powders, laser cladding powders, powders for hipping.
Right. Hot isostatic pressing.
Pressing, either near net shapes or tool steel.
What people don't realize is everything was a powder at one point. Well, not everything, but a whole lot of stuff. And a lot of the high alloys that you and I worked in, we use them in powder form because they can't be made into a wire.
True. They're very difficult to be made into a wire.
Or they're composite materials. What was that Nitung 60? Wasn't that your invention? Or?
Yeah, more or less. It's a metal matrix composite where you add a couple of different kinds of carbide to a low melting temperature matrix material so you can weld it and not melt the carbides at the same time.
Right, so you're using a chrome nickel.
Chrome boron, silicon.
Yeah, with for the matrix, and that's what we're welding. And then you have WC, W2C.
W2C, spherical carbide, depending on the application and the customer requirements.
And that makes the most wear-resistant coating that I know how to apply.
It's one of the most wear-resistant. There are other ones, titanium carbide. There are people putting diamonds in now.
Right. Yeah. We've had Jean-Marc on before, and he's doing the diamonds. Problem with diamonds is they float.
Yeah.
And so he's doing some interesting things with coating the diamonds so they'll sink. But, carbon's lightweight, and we're trying to submerge these in molten metal. So that's one of the advantages of carbide. In fact, I guess the problem is just the opposite. They tend to sink.
With the carbide, they do, and that's the trick, getting them not to sink all the way.
Right. You taught me that.
Yeah.
And, very low heat input. I remember.
If they sink all the way, then you got to machine off a matrix material that could be 60 Rockwell C before you get to the carbide.
I've done so many G65, which is the ASTM standard for wear resistance testing. I think I probably spent $50,000 on that. I blame you because...
Well, you did my first one.
Oh, did I?
Yeah, and you paid for it. Arc Specialties did the G65 wear test for Nitung 60.
And it was remarkable, as I recall.
It was the best on the market.
Yeah.
And it helped me out quite a bit. Thank you very much for that.
Oh, you're welcome. So that's a fun test. I made the weld deposit. We ran very low heat input per your specifications, sir.
Yep.
And then that kept the carbides in solution. And then we use, it's a rubber-coated wheel with sand, and you're spinning that against the part, and it slowly abrades the part, and you're measuring depth of wear and wear volume and wear weight loss.
Right. And it was a really good test. And I think one of the reasons why the Nitung was so good in that test was because you were the only one doing pulsed current plasma transferred arc.
Which seems obvious to me, but
But nobody else could do it.
Yeah, it wasn't that hard, but that's an interesting material that you came up with because I believe you created this primarily for the plastic extrusion screw industry, or was that just an early application?
That was an early application. Originally, it was done for agricultural blades.
So ground engaging wear is what we call it.
Yep.
So yeah, it's a pretty remarkable material. So you can go metal on metal, metal against rock.
Yep.
And it's also rather corrosion resistant. You're ahead of your time.
Yeah. It worked out very well. It's been around for, I think when we first did it back in, it's probably the early 90s when we first came up with it. And many versions since, and everybody's come up with their own version or copied it. And it's still out there if anybody really wants nighttime.
Yeah. Imitation is the sincerest form of flattery.
Exactly.
No, it created a whole industry for me to work in, you know, so with my plasma transferred arc, robotic welding stuff, so it's been very good to me. So I appreciate you encouraging us way back in the 90s.
Oh, my pleasure. And I've learned quite a bit from you over the years as far as torch articulation, current manipulation, doing things with plasma transferred arc that nobody's ever even thought about doing.
Well, you know what I get a kick out of hearing your stories is because since you don't have all those tools at your disposal like we have, I love to hear your stories about how you'll fix things without being able to control them. Well, I'm going to jog your memory.
Okay.
So you, let's tell our listeners, way back in the day when we were kids, we had lead in our gasoline, correct?
Correct, yeah.
Okay, tetraethyl lead, and that was placed in the gasoline to prevent detonation, to improve the octane rating, and that was critical during World War II. Problem with it is that puts lead in the air,
Right.
which decreases IQ. It's not good, and so we went. But we would probably have lead in our gasoline today if it weren't for catalytic converters.
Correct, yeah.
I'm getting to the point. It's a long story, and so the catalytic converters couldn't tolerate the lead in the fuel, so they went to unleaded fuel, which is now the youngsters don't know anything different.
Right.
But if I recall correctly, when we did that, that caused the valves in the engines to wear.
Correct, because the lead was kind of a lubricant.
Exactly.
Yeah.
And so what was the solution?
Hard-faced the valves.
Yeah, so we're actually plasma hard-facing valves.
Yep.
The Stellite company was big in that, right?
Yeah, Deloro Stellite was big. Built the machines originally to do engine valve hard-facing.
Was that Rod Weber?
Rod Weber, yeah.
Yeah, a mutual friend.
Yep. And
Bless his soul.
it's amazing. I mean, when I started getting into it and realizing how many pounds of powder were used to hard-face engine valves, it was staggering.
There's got to be a pound in each engine, right?
Well, on the valves themselves, there's only on a diesel valve, there's probably, after it's machined, maybe 40, 50 grams.
Yeah, but what does it take?
Oh, it'll take
Three times
that to weld it on, and then you got to machine it off. And then you've got some of these itty-bitty motorcycle and scooter valves that take like 40 grams to do the whole thing to begin with.
But you've sold tons and tons and tons.
It was like 500 tons a year worldwide being used for, and that's just on the exhaust valve.
And that's why I wanted to do the backstory, and it's all because we eliminated lead.
Yep.
But that's not the point I wanted to make. I remember when you were troubleshooting one of these, because I remember these stories. You were troubleshooting a valve machine, and you were getting porosity in the top part of the weld, and you couldn't figure out how to get rid of it. I don't know if it was your powder or the machine or whatever.
Yeah.
And if I remember correctly, what you did is you simply added a little extra material and made sure that the porous portion of the weld was removed in the final machining.
Yeah. Yeah.
Brilliant.
Put more down so you make sure you get it off.
Brilliant. No, I don't know when you told me that. 25 years ago.
It's got to be. Yeah, that was. I think I was in Brazil when.
Was it Brazil?
I ran into that. Yeah. Yeah. So.
Yeah, because you had nothing else you could have done.
No, not really, because the plant was in Sweden.
Right.
And we were like 12 weeks behind on deliveries.
And you were in Rio, or?
I was in Sao Paulo. Outside of Sao Paulo. And they had plants all over the world. And it was funny because the powder would work in one plant but wouldn't work in the other. And these machines were put in 30, 40 years ago. And over the years in some of these rundown facilities, the gas would be leaking somewhere, or the water would be contaminated, or the powder would have been left outside last night, or the door was open and it was blowing the shield gas away.
They didn't clean the oil off the valves or
Nothing.
Yeah.
No, they just didn't know. They weren't welders. They were machinists. So they just said, oh, this machine should do the same thing every time. But it doesn't, because you've got other factors like wind blowing and gas leaking and sucking in oxygen into the gas lines.
See, that's why I've always respected your ability to troubleshoot, because when I travel, I've got an oscilloscope in one hand, I've got an oxygen analyzer in the other hand.
I was never that lucky.
You never had the tools.
No. I think I borrowed one of your tools once.
Oh, yeah. But without it.
It was an oxygen analyzer.
Yeah. Oxygen analyzer, oh, that's a valuable tool.
Oh, yeah. Yep.
Absolutely. But because we found anything over 20 parts per million oxygen can cause problems.
Oh, absolutely, especially in a plasma.
Yeah, plasma is the pickiest process as far as gas purity goes. There's another tale. Do you remember the one about when you had too many slivers? So let's go back. Explain to our audience how you atomize powder and how you atomize and create powders.
Basically simple. You have an induction furnace. You throw the ingredients in. It's like baking a cake. You got a little chrome, a little iron, some moly, some nickel. And you bring it up to temperature, so now you got a molten bath in an induction furnace. So it's kind of stirring around. And depending on what kind of furnace you have, you're either going to pour it over into a tundish, which has a little hole at the bottom of it, about 7 millimeters. And you're going to, the gravity will force or the head pressure of the metal will force it through the hole. And then you hit it with high pressure nitrogen or argon gas. Most times it's nitrogen, unless you're doing a super alloy. Then you got to use argon. And that breaks the stream up into first a ribbon, and then the ribbon breaks off into square platelets, and then the platelets, as they're starting to solidify, pull into a sphere.
Yeah. So you're using gravity and surface tension.
To
make little metal spheres.
Yeah, and that's a lot of times you'll see metal powder that it looks like it's hollow, like a.
Sometimes it is.
Yeah. Well, that happens during the cooling phase, when these little square platelets start to curl in. They don't get all the way in before it solidifies, so now you got a hole in your powder.
So it's an art form.
Yeah.
So you're working with the Swedish Anvil company when I first met you, and
Right.
then Carpenter. And
Anvil got bought by Carpenter in 2000, and we moved the offices from New Jersey to Pittsburgh, because Carpenter in 1999 had bought a company called Dynamet, who had a titanium wire facility, and they also had a powder metal facility, and they were doing basically braze alloys, tool steels, and a lot of thermal spray alloys, and they had all aircraft approvals, whereas Anvil was all air melted stainless steel, iron base, and cobalt base.
And the problem with air melting is metals at high temperatures oxidize in the presence of oxygen.
Right.
Air has oxygen. So this really needs to be done in an inert atmosphere. And
The highest quality super alloys, anything that contains titanium, has to be done in a vacuum or an argon atmosphere, or it's going to react with the atmosphere while it's molten. The worst part about air melting is the bath has to be covered with flux, with slag, like an arc welding.
Right.
So you want to make sure you plug the hole before you start atomizing slag,
Oh, I see.
because you think that's
It'll mix.
It'll mix. It's bad.
Right, and so you know what this sounds like to me is the same way they make shotgun pellets. They melt lead, and they've got what they call a shot tower.
Yep.
And then they're dribbling this lead out, and it's like rain. It's molten metal rain.
If you ever looked inside a gas atomization tower, it's raining hell inside.
Yeah. So initially it's molten metal, and then it
Solidifies.
spheritizes and it solidifies, and then so I know that's how they do lead, but lead melts at much lower temperatures and can be done in air.
Right. A lot of shot is made that same way.
Steel shot.
Steel shot, blasting shot, shotgun shot. But when you're doing metal alloys, especially stainless steel, you want to protect them as much as you can from the atmosphere, from oxidation. And, you're doing 10,000, well, Anvil we did 10,000 pound heats. At Carpenter and Bridgeville we did up to 2,000 pound heats. So the trick is to keep the molten metal as long as you can and stop it before you start atomizing slag. And you got to check your chemistry along the way, because you have chemistry fade from the time you first get it molten till the time you're done.
Sounds like quite a science.
It is. It is.
So that's how the powders are formed, and then you've alluded to all the different uses. So there's welding, hot isostatic pressing, and thermal spray. You touched on that.
Yeah, and it's all. It's funny because they started out making powder in Enval to be extruded into seamless stainless tubing.
So it was a feedstock.
It was a feedstock. They'd make 316L stainless, put it into a big can that looked like a long cylinder. They would sip it, cold isostatic press it to get it as dense as they could, and then they would hot extrude it, and that's when it became 100% dense and seamless pipe.
I was
Kinda
unaware
like
of that.
What the guys down here were doing out, Wyman Gordon,
Right,
with the big presses.
right. They're doing something similar.
Right, right.
on this.
So that's when they started making the stainless, and then, so we had 316L coming out. We used to joke that if you worked for Enval, when you sneezed, 316L powder came out.
It's probably true.
Yeah. In hindsight.
So let's go back to atomizing. So I know from experience a lot of things can go wrong. So there's probably tricks to optimize the percentage of each given particle size. But I know that in my world, I'm looking for what, 100 over 270 mesh.
Right.
But when you guys are atomizing this, that ain't what you get. So you're getting more fines and more courses. And so one thing that happened to me once is I had a batch of powder from a company that will remain nameless, and sure enough, it was well within the specs, but all of the powder was on the fine end.
Right, right.
And that's a trick that they play on unsuspecting powder buyers. And so we were expecting a normal distribution or a bell curve.
Right, right.
And so they could sure enough say, yeah, that it is within specs, but it wasn't.
It wasn't. Well, I mean, the AWS is addressing that now.
Are they?
They're coming up with powder specs.
Bless them.
You know, for thermal spray. D2 committee was doing PTA and laser, but I think it's all fall back into the C2 committee, where there's going to be chemistry range specifications, particle size, distribution guidelines.
Mm-hmm.
You know, to where you spell out it's got to be a bell curve. You can't push everything to one side. But in manufacturing, depending on the atomizer and the nozzle's the key. You can kind of steer your powder distribution. You're always going to get a very wide distribution from 0 to 500 microns. But with different nozzle technology, you can steer it from where your main distribution would be 25 to 100 micron, and within that you can steer it one side or the other, because you've got metal injection molding, which uses 22 micron and smaller.
So they like the fine stuff.
That's the fine stuff for metal injection molding. Then your thermal spray, HVOF, HVAF, and cold spray is even finer, but that uses like a 15 to 45 or a 22 to 53.
So you got somebody to sell everything to.
Yeah, so now you got, and then the laser cladding,
What are they like?
45 to 150, and then PTA was 145 or 53 to 180. So over the years we were always cutting it up into these different sizes because that's what we sold. And then somebody calls and says, "Hey, you guys make 316L?" And we said, "Yeah." Well, we got this new thing called lens, laser energy near net shape, where we're going to make powder and we're going to use a laser and we're going to make something out of it. So we sent them our 316L, and they worked with it, and they said, that stuff was way too big. You got anything smaller? So they ended up using one of our HVOF cuts because we had it on shelf, 22 to 53.
Just relabel it.
Yep, and charge more.
So that's one way to screw up a powder, and then there's satellites, hollow spheres, oxides, and slivers.
Exactly.
I've suffered from all of these.
Yeah. Satellites is inherent with the gas atomized process. The company I'm with now, they have proprietary technology, so
You can say the name. Who are you working for?
it's Stewart Advanced Materials, and we're out of Chattanooga, and we're powder processors. We make spherical powder into flakes, but we are also the distributors for ASL, which is Atomizing Systems Limited in the UK. And they have proprietary atomization technology to where we get, and everybody says this, but I'm telling you the truth, it's satellite free.
Satellite free, because satellites are when two spheres stick together.
Yeah, they collide during atomization at the time that they're going solid.
And people, you know, in my world, that's a problem because I'm trying to feed these powders through torches, and if they're stuck together, they don't feed. We get jams.
Yep.
It's a mess.
And they can be the same size, and
Right.
they'll stand up on end and go through a screen.
Right. So they will fit through the mesh screen,
Yep.
but they are not to spec.
They're not to spec.
And the same thing happens with slivers, which I don't know how those are formed. They look
There's-
like fingernail clippings to me.
Well, a lot of those are splats. You'll get a powder particle hit the wall's ice cold, but it splats out like, you know, any liquid. When you drop it, it makes a crown. And then it'll freeze and it falls off the wall and gets mixed in with the rest of the stuff.
And it goes right through a sieve. You can't catch it.
Right through a sieve. You go through all kinds of steps to try to get rid of them.
But I remember a story how you fixed that once. Where were you? You remember this?
I was
the floor sweeper story.
I was in the,
Is that in Brazil again?
no, I was in the States.
Okay.
And we had shipped the customer a lot of nickel-based, nickel chrome silicon boron PTA powder. And there were so many slivers in this, it
Which won't feed through my torch.
won't feed through a powder feeder. They weren't even getting out of the powder feeder. They were jamming up because they were so long, and they weren't thick, but
They
they were
look like little pine needles.
yeah. And this batch was loaded with them. We did do a failure analysis.
And you can't filter them out with a screen.
Can't screen them out.
What's a boy to do?
Well, one of my friendly competitors, Rod Weber, said, go get some green, they had to be green, floor sweeping pads. They're like the reticulated foam.
Yeah.
And he said, pour it through that. He said, get like 5 or 6 of
And
them.
it'll trap them.
It'll trap them. So I went and I bought a metal pail and 6 of these 6-inch reticulated foam. I had to get green ones. Stacked them up on top of each other. The guy's looking at me. I'm looking at him. I don't think this is going to work. He says, man, give it a shot.
And it worked.
That was a customer. We poured it in, and the spherical powder went right through it like it wasn't even there. And it was like raining Christmas on the outside because all the slivers were flying out the ends of the discs
Man, you ought to patent that.
onto the floor.
You know what I do? I just reject the whole lot.
Just reject the whole lot. Now, the thing was, now after we went through, I think it was 500 pounds, got all the slivers out. Now my biggest fear is how much of this reticulated foam did I just put into this?
Yeah.
into
That's
this
probably not good.
No, but there wasn't much, but because it was lighter, I could just like swirl it around, and it all floated to the top, and then we just scoop it out with a spoon. So those are the tricks you learn in the trade. The idea is to never make those things in the first place.
Indeed. But I just love that story. I thought that was pretty cool. Particularly now that I know that it was Rod Weber.
Yeah, that was Rod gave me that hint.
Yeah, Rod actually used to back when he was with Stellite Corporation, he used to private label our machines as Stellite machines.
I know.
Yeah, and we had a great time together. And then I remember we'd travel. One time we traveled to China together, and when the Stellite machine powered on, it said ARC Specialties on the screen. It's a small world when you get to plasma, isn't it?
Oh, it is. It is. And did you ever tell anybody how plasma or why plasma came about or what the idea was to?
No, I got my version. I want to hear yours.
What do you call it? The space, NASA.
Oh, okay. Yeah, okay. So they were testing ablation coatings on the bottoms of capsules.
Yeah, because they wanted this thing to come back down. They had no idea how hot it was going to get. They figured it was going to get really hot, and they said, well, we got to duplicate the sun somehow.
Yeah.
So they come up with plasma.
Right, because the bottom of a capsule slowly burns away as you're coming through the they call it re-entry.
Right.
And then that's strictly due to friction heating from. So yeah, that was plasma.
Yep, that's how they got it. And
Okay, we got the same story.
Yeah. So there's plasma transferred arc, plasma thermal spray.
Which is non-transferred arc.
Non-transferred.
I've only done one of those. I was spraying combustor cans. This is before I met you, up at AVL in Dallas. So I tell people it's a little disturbing. The temperature that the jet plane fuel burns at is above the melting point of jet engines.
Yep. That's
So the only way that they don't come crashing out of the sky is we have to internally coat these engines with a ceramic.
correct. Yep.
And the way you do that, or the only one, I've only done it once, and that was a plasma, non-transferred spray system.
Yep.
Worked very well.
Oh yeah. All your M crawlies are sprayed through plasma. All your ceramics are sprayed through plasma. Yeah, that's the scary part about airplanes.
Hmm. And what's interesting about it, the reason they bought my machine, this was way back in the 80s, is because the thickness of that coating is critical. If it's too thin, it'll burn through the wall, and if it's too thick, it won't transfer heat properly.
Right.
I'm working off 30-year-old memories now, but too thick, it'll spall off and expose the metal and then burn through the wall.
Exactly.
So that was what, this is an early robot in the 80s, right? And so it would put down the same coating thickness every time, and that's what they're looking for.
Yep. Yeah. Yeah. All your hot components of a turbine, even land-based turbines, are all ceramic coated because they operate higher than the. And they want them to operate at even higher temperatures.
Right.
So now they're trying to come up with different alloys and different materials to push the envelope. So they burn cleaner, more fuel efficient.
Does this worry you when you're flying, or
No.
you believe in technology?
Yeah. Yeah. And then, metal injection molding.
That's how they're making a lot of the gun parts now. Right?
Yep.
Where else is? I mean, I'm trying to tell people where they're seeing this and not realizing it.
Gun parts, triggers, all small little mechanisms. Watches, back when everybody wore a watch.
Hey, I still weren't. Oh, I'm a dinosaur though.
Well, yeah, but that's a electronic watch, right?
Oh, that's metal. Is that injection molded?
Whose is it? Parts of it are.
Okay. That's a Garmin.
Swatch watch was real big on metal injection molding.
Huh.
Where you take fine metal powder, 22 micron and smaller, mix it with a polymer, injection mold it just like it's plastic. Now you've got a green part that looks just like you want it to look, except it's a little bit bigger than what it's got to be. You run it through a debind and sinter.
Which is a thermal process.
Yeah. Thermal and chemical.
And chemical.
And chemical, depending on the binder.
I see.
Some of the binders are water solvent, so you can just rinse them in water. And you more or less get rid of all the binder. Now you're sintering the powder particles together in the sintering process, and you end up with a part that's 99.8% dense in the best part.
So it has some porosity. And what's this tensile strength compared to wrought materials? Is it close?
Very close.
Huh.
Very close. But these are like a lot of jewelry and watch casings. Apple is a big user of MIM parts for the lightning plug is made with MIM. A lot of the hinges on the laptops. And when Apple comes to call, you listen because
They buy a lot of powder?
they don't necessarily buy a lot of powder, but their parts use a lot of powder. So their suppliers buy a lot of powder. So.
I see.
And then the newest thing, should we could explain about HIP?
Yeah, hot isostatic pressing.
Yeah, that's where they take metal powder, they'll put it into a can, and it will either be like a near net shaped can, or it'll be just a cylindrical can where you're going to.
This is literally a metal can made out of sheet metal.
Made out of sheet metal, welded, fill it with powder, vibrate it so you get it as full as you can. Then you draw a vacuum on it to get all the air out. And then you put it into a furnace, and you pump the furnace full of argon as high as you can pump it, normally around 3,000 psi. And then you turn on the heat.
And so that can becomes the outside of the balloon, so to speak.
The mold, yeah.
Yeah, and so then that 3,000 psi, that's 3,000 pounds per square inch of pressure, crushes that part.
Well, that's where it starts.
Okay.
Then you turn on the heat, and you expand the argon, and you'll bring the part up to,
I didn't know that.
yeah, like 0.85, 0.9 of the melting temperature. So now the part, either the powder or whatever, or the parts that are in there, are plastic. They're
Right.
in their but they're not losing their structure. As you're doing that, the pressure inside the furnace gets up around 15,000 psi.
Clever. Clever.
You can't pump it that high.
Right, you can't pump it that high, but the temperature brings it up. So now you've got pressure and heat, and all these particles stick together.
Yep.
What's the density you're saying?
100%.
100% density. So you get full strength.
Full strength. The nice thing about with hipping, especially like with tool steel or some of the super alloys that can't be formed or in any other way, you make them into powder, then you make them into the part you want.
And you get near net shape.
You can get near net shape.
And didn't you tell me once that you're making hypodermic needles out of powder?
Yes.
I didn't. So all hypodermic needles?
Well, Carpenter had an alloy, custom 465, that was made conventional and cast wrought. I think they actually went to vacuum arc reduction to get it really clean. And then they would draw it down through several processes to get it down to the diameter of a hypodermic needle.
Wow.
And then they would drill a hole in the end of it. Well, they would sell the wire to the customer. The customer would draw
They
it
would drill the hole in the hypodermic
in
needle.
the end of the hypodermic needle.
I don't want that job.
Well, it was a machine.
Okay, good.
And even though Carpenter made it as cleanly as they possibly could, when they got it down to that diameter, there was always a piece of slag or an inclusion in the wire, right where they had to drill. The scrap rate was like 30%. So now you got all this money into this itty bitty piece of metal, and now it's junk. You can't use it for anything else. And it hasn't ever been made. So they decided we're going to make powder, we're going to hip it, we're going to draw the billet down to size, and their rejection rate went from 30% to like 0.5%.
Interesting.
Because there's no slags, there's no including, there's nothing.
It's pure metal.
Pure metal. There's no drawing fluids that get wrapped up in there. Nothing. So it was a lot more money for the billet, but the customer was happy that their rejection rate went down.
But the needles don't break off in your arm.
Needles don't break off. And we had a demo of a suture that was in I think it was a 50-pound weight, and we would just hang it off the counter at the trade shows. You know, this thing was 15 thousandths diameter.
Wow.
Like a fish hook.
Super strong.
Super strong. It wouldn't, and it didn't bend. It held that up. So.
Yeah. Where else is powdered metal used that I'm unaware of?
Tool steels. Are you familiar with like powder tool steels?
All carbides, the stuff I'm familiar
Well,
with.
like they're known as CPM.
Okay, I've heard that term.
Which is crucible.
Okay, so they're making knives out of this then.
Yeah. So you take a conventional tool steel, conventionally cast and wrought, will have vanadium carbides, tungsten carbides, moly carbides throughout, which gives it its abrasive resistance and temperature resistance. But they're formed during the eutectic phase, so they're big blocky carbides, and there might be some over here, and then there might not be any, and then there might be 3 or 4 little ones over here and a couple of big ones down here.
Huh.
So depending on where you're trying to make your edge.
You may or may not have the carbides where you want them.
Right. So you have a lot of premature tool failure.
Fascinating. I know a lot of knife makers. I don't think they know this.
Oh. Well, now
I'm going to look smart next time.
Now you make it into a powder. So now that itty bitty powder particle has the same chemistry as that big block of steel.
Right, right.
So all the irregular carbides are only in this little tiny.
So it can't be far away.
Can't be far away.
Excellent.
So then you take those powder particles, hip them into a solid. They don't go molten. They just go plastic. There is prior powder boundary indications in the as-hip billet. But when you forge it and roll it, those PPPs go away. Now you've got a very strong piece of tool steel that has very evenly distributed carbides in it. So it's very easy to machine, too.
Interesting. So once again, that's what made steel work so well is we made these big billets, and they weren't perfect when you cast them, but
Right.
then we mechanically reduced them. We forged them, rolled them,
Yep.
and that tended to heal defects and reduce the. So you guys are doing the same thing in powdered metals now.
But more or less, yeah, with hipping.
And that's a problem I have with additive nowadays, is because additive doesn't get any. There's one exception. There's a fellow doing some fascinating additive with friction stir,
Yep.
and I like that because you get some mechanical deformation, which is good for metals.
Well, a lot of the additive manufacturing has been a boon for powder metallurgy.
Yeah.
And it's also been a boon for hipping.
Oh, you got to heal them.
Yeah. Yeah. In the beginning, when they were just making trinkets and toys and stuff, you didn't have to hip them. But
You didn't care about properties.
right.
Now you do.
Now you're making components. Most of the stuff that anything going to an airplane gets hipped. Anything going into medical device gets hipped. There used to be like 2 or 3 hip companies in the States. I think there's 5 now, but there's a lot of manufacturers that have bought their own hip unit because they're very expensive.
So hipping heals the defects.
Yeah.
Or reduces the
Reduces
defects.
them. Yeah, anytime you get a porosity or if you have an inclusion, it's not going to get rid of the inclusion. The inclusion's going
Right, it's still stuck in there.
still stuck in there. Gases can be squeezed out, porosity can be squeezed out. That's the main reason for hipping.
Well, I always learn something when I talk to you. I remember you used to have a shirt that said "powdered metal expert" on your sleeve, and you're my go-to guy when it comes to that. When I need something exotic, like I remember we're welding tungsten. Where do you get tungsten powder? You get molybdenum powder.
Oh,
Called
right.
Chip Arata. That's my recommendation to everybody listening. If you don't have it, you'll find it.
I'll find it for you, yeah.
Tell us, tell them the story about metal flake paint. That's another interesting story.
Oh. Well, a lot of metal flake paint uses stainless steel flake.
So that is real metal flake.
Yeah. Yeah. Well, I mean, there's copper flake, there's silver flake that's really expensive, but
Yeah, we don't do silver
yeah,
flake.
most of it's just stainless steel. There are some iron flake, but it doesn't really. It's not. It all depends on what you're trying to achieve as far as reflection. So with the stainless flake that is in paint and in sparkly plastic and even in some potato chip bags, it starts out as water atomized or gas atomized stainless steel 316L that companies will buy, and then they ball mill or jet or attrit it to turn a spherical powder particle into a cornflake. And then they have different processes along the way to control the reflectivity and the brightness of it.
And then you mix it with paint, shoot it under a car, and it looks good.
It looks good.
Yeah, yeah.
And there's some of the craziest applications I've seen are one of the major house paint companies wanted a magnetic paint,
Why?
so you could paint your kitchen wall,
And stick
knives to it, or stick magnets to
magnets to it. Did it work?
it. Yeah,
Did it rust?
I don't think so, but it worked.
You wouldn't be able to use stainlesses, is my point.
No, it was a 420 type steel.
Oh, so it's a martensitic
Martensitic
stainless,
stainless, yeah.
which is magnetic.
Yes. So, and that was crazy. And I think you can still buy that paint, but it's outrageously priced.
That's your fault.
It could be. And then we had a guy that he wanted to put metal powder into glue or into tape.
I give up.
And when you put carpeting down,
Right?
they have the 2-sided tape, and then they have their irons. Like you have the carpet, the tape's underneath. Then they have the iron that goes over and heats up the carpet and heats up the glue. So the glue now sticks to the carpet so the carpet doesn't curl up.
What's the iron do for you?
He wanted to get away from the ironing,
Oh, and make it resistance heat.
an induction coil.
Oh, induction heat.
Yeah.
Did it work?
I don't know. I sent him a bunch of stuff. I gave him a couple of ideas, and I never heard from him again.
You're probably right, because now that you're making me think of it, they have done something similar in the plastics industry where they induction heat plastic with metal powders in it. So,
Yeah.
So it's doable.
Yep. And there's a lot of magnets. There's not necessarily magnets, but it's a 400 series stainless that get mixed into plastic. It gets made into food handling components, trays, scoops.
Why?
Because if a piece of plastic breaks off, at the end of the day or at the end of the line, there's a magnet that will pick the piece of plastic out of the food because there's metal powder in the piece of plastic.
Clever.
Yeah.
Huh. And I've not heard of that one. That sounds like you've had a fun career getting to do everything from engines to jets to food.
Food and rug and paint.
Gun parts, surgical
parts.
needles.
It's been interesting. Additive manufacturing is the new thing that is, I believe in it. I don't know if it's really going to disrupt manufacturing the way
It's
that
just
they-
another tool in your toolbox.
Oh yeah, but
That's
you
the
know,
way I look at it.
but if you can make a part, aerospace, medical, the only people that can really afford
Right.
additive manufacturing.
At this point.
At this point.
Yeah. It'll get cheaper.
But they always blame the powder guy because
That's your job.
well, it's always my fault because I charge too much. Because they can buy stainless steel plate for what, $1 a pound?
Right. Where are you?
Huh?
Where's powder?
The
Stainless.
cheapest stainless powder I'm going to say is 0 to 500 micron. It's going to be $8 a pound.
But
But if you only take 20% of it to make additive manufacturing, it's going to be $20 a pound.
yeah. But then what I've found in the welding business is sometimes powders for filler materials are essential because, you know, it's a composite, can't be made otherwise, or sometimes it's cheaper.
Yeah, because, well, wire, if you look like 625 wire to 625 powder,
Which one's cheaper?
powder,
Powder. That's what I thought.
yeah. Because there's less steps to get to the finished product.
Right. Right.
Wire, you
Makes sense.
start with a melt.
So you're not always the bad guy, Chip.
No, not always, but all the new technology, like when metal injection molding came out
Yeah.
40 years ago, powder guys were the bad guys because what do you want? You know, you're charging too much for the stainless. We can buy a block of stainless and machine it out. Well, then go ahead.
Grind it up.
Yeah.
Well, it's been fun. Really enjoyed this conversation. What did we miss? What do you want to cover? This is your show.
Oh, geez. I think we've covered it all. But if you have any questions on,
Yeah, how do they find you? You know, what if I need some more molybdenum like last time?
my email is carata, C-A-R-A-T-A, at stewardmaterials.com. Or you could always get a hold of Dan, and he knows how to get a hold of me.
Indeed.
Yeah.
Well, I appreciate you coming on the show today. Next time you're in Houston, got to get you back on.
Yeah, well, I hope this makes sense to people. You just say, hey, sit down. We're going to talk about stuff.
No, it's been fascinating. And, you know, I want people to start thinking about alternatives. You know, who would have thought that throwing a little metal powder in something would make a wall magnetic? But
Oh, yeah, yeah. I mean, there's a lot of different technologies out there for the use of metal powder. I mean, the plasma transferred arc process, laser process, for cladding, weld overlay.
still plenty of room for innovation. So that's the challenge we'll throw out to our audience.
Yeah.
Get creative and think of how you might apply metal powders to one of your problems.
Yeah, for wear corrosion resistance, temperature resistance. There's a lot of reasons to, you can use a noble alloy on a cheap alloy to make it last longer and be sharper longer.
Mm-hmm.
And what was that one thing I was going to talk about was the plasma, it's not plasma transfer, it's like plasma keyhole.
Oh yeah, we build those machines.
Yeah, where you feed powder to,
Oh, that's a great idea. Yeah. Okay. So plasma keyhole is a great process. I love it.
Right.
It's funny when I tell welding engineers about plasma keyhole, they go, that's all I want to do from now. Because keyhole allows you to punch through a square joint with no bevel.
Right.
So you can imagine there's hardly, I'm not telling you anything, I'm talking to the audience here. And so you can, in effect, just make a keyhole in the part and then it heals behind the torch. It bonds together. You don't need any wire. Here's the problem. You need a little bit. And that's something you and I talked about, and I don't know if I showed you my results, but in our lab, we added a small amount of powder to a keyhole system, and it would add that little bit of powder, or that little bit of metal we needed for reinforcement. It worked extremely well.
yeah, yeah.
Great idea. All right, well, Chip, thanks for coming on.
Thanks
Next year
for
you're in
having me.
town, come back.
I sure will.
Thank you, sir.
Thanks.